continue. Is there any question, people? Is there any question about this? Any questions? Questions? Okay, good. Okay, let's go on. Before we leave, this is something which is very important, is the sign convention, okay? So in the case of beams, okay, that's, or I mean, that's the theme of our work, okay? So we have, usually you have something very long, okay? We're gonna use that as the X direction, okay? In the vertical, we're gonna have, this is the Y direction. And usually, not usually, we're going to have forces only in this direction. See, these are the external forces, okay? So in this case, we're going to need only two internal forces, okay? Those internal forces are the shear force and the bending moment, okay? And as we said before, it's very important that we agree on the sign convention. If you use different references, for example, it's classical, the difference in sign convention that there is between Popov's book and Singer's book, okay? We're going to follow Popov's, but that doesn't mean that Singer is incorrect. It's just he uses a different sign convention. So for this case, we're gonna say, okay, this is a cut, okay? Okay, here. You see that this is X direction. In this case, a normal to the surface pointing in the X direction. This is what we call a positive face. Okay, the opposite, okay, occurs if we consider this. That's going to be a negative face. Okay, now, in this positive face, I'm going to write an element here. Please, this is not in equilibrium. This is just an element which is considered show the sign convention. Okay, this is a positive phase, and this is a negative phase. In the positive phase, the shear force is going to be considered positive when it points upward. And the bending moment is going to be considered positive when it goes like this, counterclockwise. In the negative phase, see, the shear force is going to be positive, of course, opposite to this. So that's, if you have in the negative phase, you have a shear force with points downward, that's going to be considered as positive. And in the case of the bending moment, if the bending moment on the negative phase points in this direction clockwise, it's going to be called or considered as positive. Okay? This is the convention that we're going to be using at least for chapters 1, 2, and 3. Okay? At the very end of this the semester, we're going to be considering the sign convention of the Ship Classification Society, and they use a different sign convention. I will explain that later. But so far, this is the sign convention that we're going to be using. Okay? So there cannot be any doubt about this. This is just a convention. That's all. This is not equilibrium. Equilibrium will come in a minute. Okay? Here. Now, equilibrium. So I'm going to say that I'm going to consider a beam. A beam is a very long element, okay? In this class, we use this reference system, X, Y, and in this case, since we are going to be working with beams, okay, beams only, not bars, beams, we have the loads are going to be acting in this direction or can produce some bending. So these are the two loads that we're going to be working. In the vertical direction could be upward, downward, and rotation could be moments counterclockwise. Okay, so that's that. Now, let's consider now a differential element in equilibrium. Now we're talking about equilibrium. Okay, so we said, okay, let's consider this element. Okay, so we're going to take this element from here. This beam is in a static equilibrium, so this little element is also in a static equilibrium. Okay, so this is a cut at position X, and this length is dx. So you see that this cut is at position X, and this phase is a negative phase. This is not this one. It's located at X plus dx, and this is a positive phase. Now, since this is a negative phase, okay, we are going to include the positive internal forces. So we said, okay, we have a shear force V at position X, and we're going to have a bending moment here. Now, this is X. Now, if we move from here until here, okay, a distance dx, these two internal forces have changed. Okay, so on the right-hand side, we assume them positive because we do not know them, but we have to consider that they have changed. Similarly for the other. Okay, we also have force. We said is acting upward, and we're going to express this as force per unit length. This is something which is very common in engineering. Every time we use a little, in this case, little p, that means force per unit length. If we use it capital, for example, V or M, you see that these are complete forces or complete moments. Per unit force complete. Okay, that's very common. Okay, and since dx is very small, we can consider that P of X from here to there doesn't change. It's basically uniform. It's a constant value. Okay, now we can go on and we can say, if this element, or let me insist, this differential element is in equilibrium, and after solving the resulting differential equation. No. I'm sorry. I'm not writing the opposite way. Let me write the other way. Let me write the other way. The beam is in equilibrium. So any differential piece of it must also be in equilibrium. Okay, before we go on, we want to see or want to express this differential, how much changes the shear force in going from here to here. So dV, since in going from here to there, we only changing v in x. So we can say that this is dv dx times dx, and then we can go on with the Taylor series and all. But the problem with this is that this is very small, and eventually this is basically zero. What happens with this one? In the analysis, this will cancel, and at the end, this will not appear. But this one here will survive. But this is very small. This is 10 to the minus 1 million. This is basically zero. So this is very small at the end, and this is not going to be considered. This is the term that we're going to include. Similarly, the amount, the bending moment changes is the derivative, and that's it. And the other term is basically zero. So these two are going to replace here and here in equilibrium. Okay, so we say, this is something that you have to do. You said summation of forces in the y direction is zero, and this is what we apply, okay? So we obtain v plus dv minus v plus p dx is equal to zero. So these are the forces. You see on the right, I have v plus dv, and on the left, I have it v, but pointing downwards. That's what I have here. And then this is the force per unit length. If I multiply by the length, I have force. So this is force, 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 and force. And from here, I cancel this. I replace this as dv dx times dx, and this is the result. So this is a differential equation, which is equivalent to this one for a differential element. Okay? Similarly, we can take summation of moments in the z direction, okay, through an axis passing through point x plus dx. So we're taking an axis point passing through this point. So this force, the shear force in this point, doesn't have arm. So we have to consider only this one here, rotating in that direction, this one here, and the two moments. So let's use this as positive, okay? So I have mz plus dmz minus mz, okay? That's this one here, v, makes you rotate in the positive direction. So it's going to be plus v dx. And the external force, this one here, the value of the force is going to be p times dx. And the arm is going to be from here to here. So it's going to be dx over 2. So it's going to be minus p dx times dx over 2. And that's equal to 0. We cancel this. This one here is dmz dx times dx. And we can see that we can cancel a dx from this guy here. The problem is that here, dx is very small. So this is differential. So this is approximately equal to 0. And from here, you take v to the right-hand side, and this is the expression that we obtain. So in here, this expression represents summation of moments in the z direction. Okay? And but in the differential way. This is summation of forces in the vertical direction in differential way. Now, what we can do is we can replace this into here, and this is the result. So this is an equilibrium equation in differential form A beam. Something which is very important, it's something that I insist all the time, are the units. Okay, in this case, What are the units of the first term? Mr. Ramirez, Jose Ramirez. What are the units of this term? The second moment of the second derivative of the bending moment. What are the units of this? Okay. What are the units of the second derivative of x with respect to x of the bending moment? No, Mr. Chicaiza?
I think.
For example, Mr. Chicaiza, when I remember in dynamics, okay, when you have the acceleration, again, you say that's the second derivative of v with respect to time.
Yes.
Okay. What are the units of acceleration?
Second. No, sorry.
Come on, God. I should kill you. I should kill you.
Sorry.
That makes no sense that you don't recall the units of the acceleration. Come on.
Length over time square.
Exactly. Come on, people. You shouldn't doubt this. Okay, so we take this, that the units of that is length. We take that, the units of that is t squared. Similarly here, okay? That's something that you did in physics, I guess, if you didn't copy. In here, what are the units of this? So we said, okay, we have moment to the first power. What are the units of the moment?
Force per length.
Times length. And then in the denominator, we have length
Length square.
squared. So we cancel one length, and the result is force per length. On the right-hand side, those are the units of P. We said that P of X, little p of X, is the force per unit length in the vertical direction. So potatoes, potatoes. Every time we do an analysis, we have to, we have to check the units every time. So it's extremely important, okay? Something which I didn't mention, let me go back when we talk about sign convention, is that here, the positive bending moment, you see, it's doing something like this, right? The positive bending moment. So the positive bending moment makes you generate something like this. So this is positive bending moment, positive bending moment, right? On the positive and on the negative phase. And you see that it's like something, somebody would be smiling. And many times you read that they use the smiling beam sign convention. Okay, so when you have a positive bending moment, the beam tends to smile. The opposite, when the bending moment is negative, then the beam is sad, okay? Which is something very, very useful when we check the results. I forgot to mention that, I'm sorry. Okay, so we are here, and that's it. So this equation, the second derivative of the bending moment is equal to P of X. It can be used if we want to analyze systems which can be solved only with equilibrium equations. How do you call a system which can be solved using equilibrium equations? How do you call that kind of system? Mr. Benavides, how do you call that system? How do you call that system?
I can call that no determinated.
No, determinated.
Determinated.
Exactly. So this can be employed or statically determinate systems. Okay, and you ask yourself, what would happen if I have a more complex system? Don't worry, we will solve that in the next subchapter. In that case, yes, we will need something extra. And an extra is going to be a combination of the kinematic assumption, Hooke's law, and a simplification for the curvature. So this equation, equilibrium, we can use it to calculate systems with, statically determinate systems only, okay? If we have to analyze in a statically indeterminate systems, in that case, this equation is not enough, okay? It's, as we said, as we did in the previous example, if you have more than reactions, that the number of equations that you can apply, you cannot solve that system. That's the same idea, that's equivalent, but in the differential way. Okay, now here, I'm sorry, let me go back here. I have, this is the external force, right? This is P of X. This is this force, it's P of X. This is P of X. And it's expressed as force per unit length. That's what it represents, force per unit length. The problem is that many cases we have concentrated forces, okay? With concentrated force, very often. And the problem is that when we have concentrated forces, is that usually the requirement, the structural requirements from the structure is very high. So it's very interesting to be able to analyze this type of situations. Okay, so what can we do in that case? Okay, there are many ways. This is only one way, uses Popov, and that's what we use here. Okay, so what we can do is we can represent these concentrated forces using a delta Dirac function. Okay, so here, for example, let's suppose that this is a delta Dirac function. Okay, so the delta Dirac function is a function which values 0 outside the point when it is applied. You see that there is no value here of the function and there is no value here of the function, except here. In here, this is very high. So basically this is infinite value. But the area under this, this spike is equal to 1, okay? So if you consider that this is a function, okay, per unit length, the area under that function is equal to the integral, and that's going to be exactly 1. Okay, that's which is very interesting. And this is the way we represent it. This is the delta sign, be careful, x minus a. This implies that it is applied at point A. Okay, now, what happens if we integrate this function? Well, this is the thing, okay? When we integrate it, like in this case, okay, if we integrate from, for example, from 0 until here, this area is 0. So there is no area. If you reach this point here, the area is still 0. And that's what we're saying here. If you integrate from 0 to x, and x is to the left of a, even up to here, there is no area here. And the integration gives you 0. But if you integrate up to here, see, of course you have nothing here, but here you have the area under this spike. And by definition, this area is 1. And after that, here again, the area below this function is 0. So if you go up to here, you have no area, you have 1, and from that point, you do not increase. So you can say that if x is higher than 1, larger than 1, the result of this integration is going to be 1. And this is what we call the step function, okay? So instead of writing all of this, we write it like this. the integration of the delta Dirac function is a step function. This function values 0 to the left of A and values 1 to the right of A. Okay, so that's the result of the integration. Now, this is very important. Okay, these are units. The units are extremely important. Okay, so if the result is 1, this is non-dimensional. The dx, the differential x, has units of length. So that means that definitely this function needs to have units of 1 over L. So the product will give you something which is non-dimensional. Okay? Now, in the previous slide here, we have a second order differential equation. So here, it is possible that we need to integrate twice. So if we need to integrate the step function, okay, the step function, I'm going to write it here. Let me change color. I don't want to use a very strong color. So I'm going to plot down here the step function. So it values 0, as you can see here, and then here it jumps 1. And again, if you integrate from 0 to a, the step function up to here, there is no area here. If you integrate up to here, then this area has to be included. Okay, so this is point A, this is point X. So this distance from here to here is X, and the height is 1. So the area is this one. So this function here can be expressed as this one. It is equal to 0 because there is no area here when X is less than A. And it has to be equal to X minus A when X is larger than A. Okay? And this, you can write it in a more compact way, like, so the integration, see, of this, instead of writing all of this, we write it like this. So if this is, you want to evaluate this integral with up to a value of X, which is less than 0, then the step function will value 0. And the result is going to be 0, which is this one here. If you want to integrate up to here, in that case, this step function will value 1, and you will get this result, which is this one here. So this is a very compact way to express the integration of the step function. Okay, so that's the way we do these things. Okay. Jesus. In more space. Okay, this integration, let me open a new page.
Excuse me, doctor. I have a question.
Just a second. I'll come back to you. Just a second, please. Okay, go on. Ask me a question.
Okay, doctor. For the delta Dirac function, so we don't consider the reaction in the end.
No, don't worry. I'm just
the point A, B.
No. I'm just trying to represent the integration. I'm not saying anything about that yet. See, that's yours. If you have a concentrated forces, this is the way we can analyze it. That's all what I'm saying. Okay. Okay. I'll come back to this in a minute. Right now, are you seeing my projection, people?
Yes.
Yes,
Yes,
doctor, but not in the full screen.
Let's see if I can. Okay, now. I can this in a very elegant way. Change color here. So let's suppose that x is higher than a, right? So what I can say is I can change this integral and integrate it from 0 to a. Integrate from x on, I'm sorry, from a until x. Right? How much is this one here? How much is this? Anybody?
0.
0.
Yes, because you are to the left of a. And how much is this one here?
1.
1. Because you are to the right of a. Okay, now, if we have this, you can say that this is from a to x dx. And what we can do is we can do a change in variables, okay? So we can define, for example, a variable z, define it at x minus a. Okay, in this case, we can say that dz is equal to dx, I'm sorry, because a is a constant. So we can change this, okay? Instead of x equal a, when x equal a, z is equal to 0. So we call z from 0 until z, and which is x minus a. Instead of dx, I put dz like this. This is x minus a. Okay, so this can help you if you try to integrate this one more time. Okay, so integrating the ramp function. Okay, so we want to integrate the ramp. The ramp function is equal to is x minus a step at a. So you want to integrate that, okay? So we integrate that from 0 to x minus a, step at a dx. Again, we separate this integration from 0 to a and from a to x. Okay, this is 0. Now here, we have the step function. The step function in this region is equal to 1. So this is equal to the integration from a to x of x minus a dx. Because the step function in this region is equal to 1. Now here, we do the same change in variables. So we go the integration from zeta equal to 0 until zeta. Now, x minus a is zeta, so this is zeta, and dx is equal to d zeta, so this is d zeta. And this is equal to zeta squared over 2, from 0 to x minus a. So at the end, this is going to be x minus a squared over 2. So if we want to summarize this, we're assuming that x is larger than a. So what we can do is we can express the integral saying that this is equal to x minus a squared divided by 2 when x is larger than a. If x is less than a, the whole integration will give you 0. So this way, we can integrate the ramp function. Question for you. What would you obtain if you integrate this one more time? Because in the next subchapter, we have to integrate this one more time. What do you think you are going to obtain if you integrate this one more time? Anybody?
That result should be x minus a to the third
Okay.
over 6th.
Exactly, over 6. Multiplied by
step function x minus a.
minus a. Exactly. That's what you're going to obtain. And we need that integral. In a minute, you will see. Okay, let's go on. Here is, we have an example. Okay, we have an example then that we can solve. Okay, so we have 10 minutes, so we have to solve it in 10 minutes. This is something that you did probably in the past, so it shouldn't take us long. Okay, now, we have this beam. There is a support here, simply supported here. Oh, I'm sorry. And we have a moment. This is an external moment on the end. Okay, now, this is, let's suppose that we can solve it using our differential equation. Okay, of course, you can do summation of forces, summation of moments, you can calculate the reactions. But the point is that we can solve that using our differential equation. And you will get ready next subchapter. Okay, in that case, we're going to work with indeterminate systems. And the equilibrium equation is not going to be enough. So it's a good idea if from now you start practicing solving this differential equation for the solution. Okay, so we say this is the equation we want to solve. On the right-hand side, we have P of X, right? Now, here, you see that I got like this and like that. That means that inside, this is the domain. And the domain has to satisfy equilibrium. Here, I have, this is a boundary, and this is also a boundary. You see that M0 is outside the domain. So in this case, you can consider it inside, but it's, for me, it's easier if I take it as part of the boundary. What happens with R sub B? Well, in general, we're going to have a reaction, R sub B, and it's going to appear inside the domain. So if it is inside the domain, it has to be included in the P of X. But it's a concentrated force. So this is the way we're going to write it. It's equal to R sub B delta Dirac at point A. So you see that this has units of force. We said before that the delta Dirac has units of 1 over L, so everything is correct. So this is to be satisfied inside the domain. Now, we have to agree on something. See, if we integrate, we're going to have two constants of integration, right? So we need two boundary conditions. If we have two boundary conditions, two constants of integration, we can solve the problem. The problem in this case is that we have another unknown, which is the reaction. Okay, so in this case, so if we need to solve this, we need equations. Okay, so in this case, you can see that in this point, it's simply supported. And here, it's free, but it has a concentrated moment. So on the left, it has a pin, okay? On x equals 0, there is a pin. So there is no opposition to rotation. If the beam wants to rotate, it can do it freely, no opposition. So the bending moment at this point has to be equal to 0. On x equal L, see on this point here, okay, the shear force is 0 because there's nothing here. I mean, if this point wants to move downward or upward, there is no support to avoid that motion. That means that the shear force has to be 0. But we go back and recall that the shear force is equal to the negative of the first moment of the bending moment. So we can say here that the shear force at L is equal to the negative of the bending moment at L is equal to 0. So that's another condition. And finally, we have this external moment. Okay? Now, this external moment, we have to be a little bit careful. That's all. Okay? So let's suppose that we have the end. This is the end point. And in this point, I have M0. So up to here is, I'm sorry, up to here is L. Now, question for you. Is this a negative or positive phase?
Negative.
The bending moment here is going to be counter or clockwise? Positive.
Clockwise.
Clockwise. So why do we put it positive? Because we do not know it. So if we do not know something, we pull it positive. So please be careful. This is a negative phase, and we take it as positive. This is an external moment. This is a condition. The external moment in their values M0. That's a value that we know. If this little piece has to be in equilibrium, these two moments have to cancel each other. So we can say that M0 minus the bending moment at L, they have to cancel each other, so they have to be equal to 0. That means that the bending moment at L has to be equal to M0. So please, this is something from your differential equation class. You have a second order differential equation for the bending moment. So bending moment, that's the function that we're trying to determine. Okay? Second order, so we would need two boundary conditions for the constants. In this case, we do not know the reaction. That's why we need to include three conditions. Okay? There will be cases when you do not have enough boundary conditions to solve it. And in that case, we're going to differentiate in the next session. We're going to differentiate from statically indeterminate beam cases. And in that case, this equation is not enough to solve it. But in this case, it's okay. So we have two constants of integration, one reaction, so that's three unknowns. And this is what we have done. We have imposed three boundary conditions so we can solve it. Since the function that we try to determine is the bending moment, those boundary conditions has to be the values of the bending moment or the first derivative of the bending moment. Yeah, but the first derivative of the bending moment is the shear force. So in this case, we have a complete problem and we can proceed to integration. Let's do just one step of integration. Okay? So here, we have the second derivative. It's equal to the reaction delta Dirac at A. We integrate, so we say dmz dx is equal integration of the delta Dirac function? Is the step function. We know that. But we have to include one integral. If we integrate one more time, we say MC is equal to, what's the integration of this? That's the ramp function. So we have 1, 2, and 3 unknowns. We have 3 boundary conditions. We should be able to solve it. So we apply the 3 conditions: bending moment at 0, shear force at L, and bending moment at L, and there. So I'm going to do the first one, and you have to complete no, you complete it in class, as a homework. Any questions, people? Any questions about this? Any questions? No? Okay, please. I would like you to review in your class notes, and you have to tell me, what do we mean by kinematic hypothesis? I'm going to publish this so you can know. Oh, there's no time for tomorrow. No, please, everybody has to review about the kinematic hypothesis from your class notes in solid mechanics, okay? And then you have to review how to calculate the inertia of composite sections, okay? Usually here, what we do is we use a table in order to calculate it, okay? But this is something that appears extremely often. That's why this is a good idea that you remember how to calculate it, okay? This is something that you have to remember all the time. So for tomorrow, at what time is the class? Anybody? What time is the class tomorrow?
7 a.m. to 11:30.
10:30. Okay, on 10:30, we're going to review this kinematic hypothesis. Well, first I'm going to check the values of these constants, okay? Then I'm going to ask you about, or that you explain to me, what is the kinematic hypothesis? And then we're going to reduce an expression for the normal stress in beam bending. And in this expression will appear the inertia. And then we're going to review how to calculate the inertia of composite sections. Okay? All of that for tomorrow. 10:30. Okay, if there's no more questions, then I'll see you tomorrow. Please don't forget, if you are interested in receiving a copy of the class notes, printed version of the class notes, to send an email to Andy or Daniela Sayo, and so we will know by the weekend how many copies do we need. And in that case, over the weekend, I will ask to make copies. So we need the number, of course. Mr. Zurita, hello, Mr. Zurita. Is there anything interesting about today's lecture that you remember? Anything interesting about today's lecture? Something that you liked this morning?
Yeah.
Anything interesting? What is it? Or was it boring? What is it that you like the most today? No, nothing interesting. Okay, good. Could be, of course. Mr. Aizaga, what did you like the most this morning?
The part of the
analysis of the structure, the forces.
Okay, that's interesting. Yeah. Mr. Paredes, what did you like? Do you remember anything special from today's session? Daniel Paredes, do you remember anything special from today's session?
Good morning, doctor. Right now, I am in my job. I listen your class.
That's not my question. That's not my question. That's not my question. Mr. Soria, do you remember anything interesting from today's session? Mr. Soria? Anything interesting from today's session? No? Ms. Valdez, anything interesting from today's session?
The internal force in the body, how
Okay.
they act to maintain equilibrium.
Ms. Avilés, if you have the negative phase, the shear force is positive upward or downward?
Downward.
Okay, good. That's something that you should have in your memory. Okay, people, see you tomorrow, 10:30. Bye-bye now.